Okay, unplug the hot plate. Boiling water in here. What's in here besides liquid and gas phase water? A little bit of air, right? Well, when I do this, then steam is pushing the air out. When I stopper it up, turn it over, is it still boiling? No. Okay. Oh, wait a minute. Is it still boiling? Why? It's still hot, right? It's still nearly boiling because I just took it off the heater. Well, it's boiling because the vapor pressure of water, the amount of gas vapor, water vapor that this solution or this liquid can provide is still higher than the pressure inside the flask, even though I'm not heating it. Now what happens if you take a pot of water, if you're about to make spaghetti, and then your roommate says, hey, let's order a pizza instead, but you've got the water boiling already, so you take the pot of hot water off the stove. What happens? It's boiling immediately, right? When you're not putting heat into it anymore, or pretty quick. Well, this is starting to slow down its boiling, but let's see if we can boil it more by putting some ice on it. What is happening here? It's obviously boiling more than it was, isn't it? Why? Well, what's happening is that because there's ice in the little concave bottom of this thing, which is now the top, of course, can you see what's happening in the center? We're getting some drips. Right. We're getting condensation on the concave surface here. That condensation is decreasing the amount of water vapor inside the flask. And so as the water vapor inside the flask keeps condensing, the pressure inside the flask is low, but the water can still make vapor pressure that's fairly high. Okay? So by having the ability to make a lot of vapor pressure of the water, because the water is still quite hot, and remember water has a pretty high specific heat, I can use that high vapor pressure of water to make bubbles, even when the temperature of the water itself is quite cool. It's not quite cool yet, it's still pretty hot. We used to do this with a thermometer inside the flask, but it looked too much like there were bubbles coming from the edge of the thermometer hole, so we don't have that anymore. It would be kind of cool to see that. I did once get it down to still boiling at 30 degrees C, which is below body temperature. Okay. And you can see also that the ice is melting pretty fast in here. Why is the ice melting so fast? What's making the ice melt? Well, we're giving it heat, right? Where's the heat coming from?
Water vapor.
Yeah, it's the water vapor condensing, and of course bits of water splashing up onto the thing too, but mostly water vapor condensing. Okay. So what's the direction of heat for all of these changes? Well, anytime we're decreasing the amount of kinetic energy in something, we're releasing heat. So if we say, let's just do the sign of delta H for each of these 6 things. If you melt something, does that take heat or does that give off heat? So delta H is positive. How about freezing? Opposite process, opposite sign. How about evaporating water? Does it take heat to evaporate water? Yes. So that would be endothermic, delta H is positive. Condensing, delta H is negative. Subliming, to go from a solid to a gas, is that exothermic or endothermic? Endothermic, we have to give the gas a lot more energy here. So that's positive. And then the opposite, deposition, is exothermic. Okay. Now, if you are interested in weather, why do hurricanes form and so forth, that has a lot to do with the energy of water vapor condensing. We get big thunderstorms because of the heat released as a very humid air cools off, condenses to liquid water, releases more heat, and builds up those great big thunderheads. Okay, we will continue with phase changes and vapor pressure on Monday and blow some more stuff up.